Okie dokie artichokes. I'm taking this whole forces unit and splitting it up into 4 different topic videos. They're going to be on the shorter side, but at least it allows me to focus more on specific aspects of our forces unit, specific topics. And this one is going to be about the basics of forces and Newton's 3 laws of motion. Alright, let's start. So we're going to start with this idea that force is a type of vector quantity. And we represent it with the variable F in equations. And the unit for force is Newton, after the physicist, mathematician, Sir Isaac Newton. And we abbreviate Newton with capital N. There are 2 types of forces we have: action at a distance and contact forces. So the common type that we usually encounter are contact forces. So if we have an object right here, and you apply a force to push it, and it moves along, well, that's a contact forces, because it requires contact between the 2 interacting objects. Whereas action at a distance, you could apply a force to the object to move, but you don't have to be in direct contact. You could apply it from a distance. So that's why it's called action at a distance. For example, action at a distance force would be like gravity. You could also talk about magnetism, magnetic forces, or electrostatic forces. Whereas contact forces, which is we commonly look at, such as friction, tension, and even normal force. These are examples of contact forces. And so we have all these different types of forces, and what happens when you have multiple forces acting on a single object or the system? So that's what we call the net force. It is the vector sum of all of these forces acting on the system, and this system can be composed of either one object or even multiple objects. So if you have multiple objects, then you have to take into account all of the masses in play. Alright, and this net force causes the acceleration. So forces are responsible for changes in motion, and it's really this net force, this overall net force, that causes the acceleration of objects, changes in motion. Okay, and when you have multiple forces in play, it's useful to use what we call free body diagrams, which is essentially you're drawing and representing the object as a box, and you're just drawing all these vector arrows to represent the different forces. Something like here, go here, here, and etc. And so when we say vector sum, that means when you have 2 forces acting in opposite directions, you need to take into account the differences in these directions. So if you have 10 going here, 10 newtons going over here, and 3 newtons going over here, then your net force will be 7 newtons to the right. So you need to take into account magnitude and direction. But on the other hand, if you have 2 forces acting in the same direction, this one being 5 newtons and this one being 3 newtons, then you need to add them together, because it's as if you're having 2 different forces pushing together in the same direction, so they add up to make a stronger force. So your net force in this case would be 8 newtons going down. Alright? So after determining this net force, if you do have a net force with a certain direction, then the objects will accelerate in that specific direction. Okay? Now what happens, like in our first example right here, this guy. What happens if you have numbers like 8 newtons here, 8 newtons there, 8 newtons there, and 8 newtons there? You see that the left and right are equal, they cancel each other out. And you see the top and bottom there also cancel each other out. So in that case, you have a net force of 0 newtons. So when you have opposing sides being equal to each other, they cancel each other out, and therefore you have no net force. And when you have no net force, you also have no acceleration. And then this leads us into Newton's first law. Net forces cause changes in motion. So if you have a net force that's not 0 meters, 0 newtons, then you do have an acceleration. But if you have no net force, where net force here is equal to 0 newtons, then you do have no change in motion. That means 0 newtons means 0 acceleration. And the object is in what we call equilibrium. It's a state called equilibrium where all the forces are balanced. Everything cancels each other out. They account for each other. They counteract each other. And then before we even talk about the different states of equilibrium, we need to talk about inertia, because Newton's first law talks about objects in motion stays in motion, objects at rest stay at rest. So they stay in the equilibrium state until you have an unbalanced net force causing that change. And that change in motion is dependent on its inertia, which is the tendency to resist changes in motion. Inertia here is directly related to mass. So that means the higher the mass, the higher the inertia. It's not dependent on anything else, it's all mass. So speed has no effect on inertia, just mass. And then we have two states of equilibrium, static and dynamic. Static meaning at rest, whereas dynamic meaning constant motion. Same speed, same direction. Alright? And so in both of these cases, you have 0 net force is 0 acceleration. So it's important to look for those key words that indicate that the object is in equilibrium, whether it's at rest, staying at a constant velocity, constant speed, not changing its motion at all. Now let's talk about when you do have a net force. So Newton's second law is about F net equals ma. So this talks about the relationships between these three variables, and it's all about the acceleration of objects, how it's related to both the mass and the net force. So when we rearrange this equation to get acceleration by itself, you're going to get A is equal to F net over m. So the more force you apply, the more acceleration you're going to get out of that object. Whereas the more mass you have, the greater the inertia, the greater resistance to change. That means the lower the acceleration. Alright? So if you apply the same force to two different objects of different masses, then clearly the smaller object will go further out and accelerate at a faster rate than would the bigger object with the bigger mass. Okay? So this equation is only valid when you're talking about looking for acceleration, if you're looking for net force, if you have a net force. Alright? Now I have to also talk about this other type of force, weight. It's also known as the force of gravity. So weight and force of gravity are used interchangeably to mean the same thing. And it's given by this equation, F of g. So this g stands for the force of gravity, because we're going to deal with different forces, so we need all these little subscripts to indicate which type of force we're talking about. And then g here is acceleration due to gravity. Whereas this m here is mass. So the acceleration due to gravity, specifically on Earth, it's 9.81. If you're somewhere else, you need to solve for that, or they give it to you. And so it's important to know that mass and weight are not the same thing. They're two different things. Mass is represented as m, weight is F of g. So this is a variable. Let's also talk about their unit. The unit for mass is kilograms, just as the unit for weight, like any other force, is Newton. Is it location dependent? Let's talk about that. Mass isn't, but weight, yes. So weight is dependent on gravity. That's why it's location dependent. If you go to different locations, like let's say the moon has weaker gravity than Earth. So because it has weaker gravity, people or any other mass would weigh less on the moon. Versus if you go to Jupiter, it has stronger gravity than Earth, so you're going to weigh more. Mass, on the other hand, is all about the stuff inside of you, the stuff, the matter. So your matter, the amount of matter in you is not going to change. That's why it's not location dependent. It won't change wherever you go. The only way it'll change is if you lose an arm on the way to, like, let's say the moon. So that's the only way your mass would change, is if you lose any parts of yourself. Okay? And then we have Newton's third law, the last of the three. So it talks about force pair interactions, action-reaction. So any two forces that are interacting with each other are always equal in magnitude but opposite in direction. So key words you need to look out for are the pairs of objects. So you need to look out if they're the same two objects. So if object A exerts a force on B of 10 newtons, then object B will also exert a force back on object A that's also 10 newtons, but opposite in direction. Equal in magnitude, but opposite in direction. And there are two types of reaction forces that we learned about in class: tension force and normal force. Tension is related to cables and wires and string. So if you have an object hanging by a string or a cable, like we typically use in lab, you're going to have the weight of the object pulling down, but in response to that, the tension force will pull back up, causing the object to be stabilized. And then you have the normal force, and that's for objects resting on surfaces. So the weight, again, is pulling down, pushing down on the surface, but in response, the surface is going to push back up with a force to help stabilize the object on the surface, equal in magnitude but opposite in direction.